really honored to introduce DAMEN for the today keynote. Dima is a full professor at the University of Bristol. She did a PhD in Leeds in 2009, actually. And she's the recipient of one of the most important award and grant in UK, EPSRC Early Stage Career. Dima is a very influential person in egocentric vision. She started with this big project called Epic Kitchens, which is now spread worldwide and has given many, many ideas to other new projects on this context. And she's going to tell us what is happening on video understanding in egocentric vision. Thank you, Dima, for joining us in Italy.
To today's keynote, and I hope you're gonna see that it is worth it. Closer? Okay. Right, so in today's talk, I'm gonna be telling you about video understanding, which is a very, very hot topic in general in computer vision. You know, the claim is we've solved images, but we haven't yet solved video. You do hear that all the time. And maybe we'll start by kind of saying, what really is video? Because if we looked at all the types of videos we have around that we would wish to analyze and learn from, and we split them by the perspective, where is the camera relative to the action? And typically there are these two words, third person versus first person or egocentric. And also we split them by how much editing the video had experienced before it gets to the stage of being used for learning. Then some of you might remember that we started by movies as the way of understanding the world. So video understanding, the first couple of data sets and papers were actually capturing people sitting down and drinking in movies. And movies is hugely edited. It's actually scripted. The camera is in a certain position where the person is actually acting that particular scene. Slowly, people started thinking, okay, maybe there are more interesting videos out there. And sports, UCF 101, UCF Sports, were all about this TV type of footage. Again, this is still curated in the sense that there's less acting, but the camera really takes specific shots throughout the scene, and it tends to be generally cut between different viewpoints. Then slowly, we started seeing the influx of people capturing more and more videos, making them available online, mobile recordings, and the extreme thing of live streaming. All of that is still in the perspective of third person. That means there is an action taking place and a camera a bit further capturing that action from an observer or a viewpoint perspective. Recently, there are more videos that are showcasing stuff a little bit closer to where the action takes place. So the how-to videos we all get used to checking on YouTube tend to kind of have a closer viewpoint to people doing actions, maybe a top-down view of someone cooking or making a particular craft. Vlogs, which is people now recording their daily life and explaining how they do things, usually with lots of talking. And in this talk, I'm going to be telling you about something a little bit on that side compared to movies. So things captured from the first-person perspective, and they haven't been edited at all. And maybe the best thing is to start by showing you a bit of what this looks like. So this is a bit sped up, because otherwise life is really extremely boring. So these are people in their kitchens wearing a camera and going around doing everything they could do, from washing the dishes to preparing meals to putting stuff away. Why are these types of footage interesting? You know, what can we do with it? We can really understand actions and objects from the perspective of the human. Imitation learning is a big thing, you know, if I can recognize it from the perspective of the person actually doing the action. And that's probably what most of egocentric vision is about at the moment. But there are other really interesting questions, like how did the person perform that particular action? What tools have they used? How experienced that they are in doing the action? Why are they doing this? You know, what is the eventual goal? Can I understand what they might be doing next? And maybe assistive technologies is a big thing. When exactly have they done it? And if you want to do any sort of assistive technology, the when is really important. If you don't provide advice on the right time, it probably is too late. And of course, where is the person relative to the big environment? So mapping a world or tracking the person and what they do in the world. And there is work at various stages in all these topics. There isn't yet work in analyzing the camera wearer. What do they feel? What do they need? What's their personality? But with more and more footage of this type appearing, I have a feeling that this is going to be a very hot topic for people trying to understand the camera wearer. Right. So a few years ago, we started with this big project called Epic Kitchens at Bristol, Catania, and Toronto. And what we wanted to do is to capture this footage, because we didn't yet have the type of cameras that will allow us to capture this type of footage. So we basically took cameras, gave them to individuals, asked them to take it to their homes, and record everything they've done in their kitchen for 3 days. Basically, put the camera on your head, and then start it as soon as you walk into the kitchen, and only stop it as you're stepping out of the kitchen. And this type of free data collection gives you this perspective of the world, but it's impossible to annotate. How on earth would you annotate 2 hours of someone making a recipe? Inspired by success in movie analysis, we then went and asked people after the recording to watch their videos and to give us what we thought was like a live narration, a subtitle. But that's not while they're doing the action. The action was captured, completely unscripted. But after that, they would sit in front of the video and give us this live narration, from which we were able to actually do efficient, dense action segments, because we just needed to refine the start and end time around the sentences. And in 2018, we released what now is called Epic Kitchens 55, so 55 hours of this type of footage. And of course, you never do it perfectly the first time. So we went and did an extended data collection. We went to the same individuals as well as new individuals. Some were still in their kitchen, some had moved house. We asked them to collect for us again. We improved the way we collect our narrations. We improved all our annotations, densities, without not missing any action. It's always interesting when you ask people to narrate, they remember some actions and not others. They tell you about opening a cupboard, but they forget about closing it because their mind had already moved into the next action. So we went and improved all these annotations, and for a couple of years now, the community has been working with Epic Kitchens 100, which is improved in scaling and in density. So, of course, it's very hard to think about collecting a data set, and we didn't want to collect yet another large-scale data set, because typically the problem in machine learning in practice is that we start with a research problem. So I want to solve, say, object recognition. Let me collect a data set for my particular task. Object recognition, let's take the ImageNet style, you find the hierarchy of actual classes, then you go and try to find a number of examples for each class. You can clean it or have it less clean, weakly supervised, put it in this big data set. And with time, we just train this model. We realize the error we're having, and we spend years and years trying to, optimize that error, do better and better and better over time. And then, and we know that for people who've been in the field for a while, and the bigger data set comes, and it showcases that we haven't solved that problem, and we start the process again. And this applies to most of the data sets collected for machine learning research. That methods really tend to overfit to the data set, and data sets are designed to be useful for one task, which results in lots of biases by the choice of researchers, and very critically, they become unnaturally balanced. So you collect 100 examples of a dog and 100 examples of a baboon, and that's really not the numbers of these species in the world. When we did Epic Kitchen, there was one exception to this trend of collecting a data set for a purpose, and that was the Kitty dataset. So the Kitty dataset, for those in autonomous driving, is transformative in the field because what they did is they said, let's collect footage, and then we'll see what types of problems we can try to solve out of the wealth of possible problems. So when they collected Kitty, the set of tasks at the bottom were not really designed. First, they collected the data, and then they designed the methods. And that's what we wanted to say. Okay, let's collect the data and worry later about what we can use it for. And that was Epic Kitchens. We just gave people cameras and said, record what you've done in the world. And, eventually what we have is footage like this. And the footage is giving us ideas about what we can do. So I think there are lots of works that are now trying to capture errors or mistakes or people actually not doing things right. And if we designed the collection for, say, action recognition, we would not have even captured this part of daily life. So one of our biggest challenges was coming up with these narrations or subtitles. And I remember, originally we said people are going to sit in front of the footage and record these short segments explaining when they've done something. And then I realized for people, even if they've been in the UK for 20 years, they don't know the name of that utensil in English, ever. They never needed that. And so quickly we realized people had to narrate in their native language. That wasn't an original plan, because otherwise we were not getting ground truth. People were just giving us words of things. They thought this is the name of that utensil or that cookery. So we ended up actually with a multilingual data set that is out there for those who want to do some stuff. It's only recorded one language per video with the native language of the speaker, Spanish, Greek, Italian, and Chinese, in addition to English. And from these, we went and refined, as I said, the start and end time, producing footage like this, right? So you have all these examples of people opening an oven, captured in their perspective. I like the one on the top left because you can see the heat, the blow of the heat as the oven is really hot. And this type of footage, if we had designed it, we wouldn't have gotten this type of natural footage. And it was really exciting for us, of course, realizing how we knew, but realizing how unbalanced the world is. So these are actions in the data set, which we've grouped into a bit of macro classes, and the y-axis here is log scale. So of course, you do something a lot more than others, and similarly for objects. So this is a data set we've collected. Currently, we have 5 open challenges, deadline coming soon, and this will be the 4th time we're awarding winners. Last year, we awarded winners virtually, and we're looking forward this time to finally, again, awarding winners in person. So the action recognition challenge is now, from this complex data set, we still had to simplify that so that the community is interested. Because if you give them 2 hours of video, they're like, what do we do with it? So we have these simplified challenges where, for example, in action recognition, we've given people the short start and end time out of this long clip. And we just asked them to say, what is the verb and what's the noun, what's the action, right? So there was a lot of effort actually making sure this complex data set is close to what we're doing at the moment, but also has this open questions that enables questions beyond action recognition. And we have, of course, a leaderboard that people can submit to. So I'm not going to talk more about Epic Kitchens, but it's the base of some of the ideas that I'll tell you about. One of them, like my dream when we collected the data set, is that these single timestamps, which is 1 point in time with a sentence, is enough for us to learn, right? Why do we need to go and do the expensive task of localizing start and end times and then mapping the free form into languages? And that was one of the first works we've done, which is let's start with these rough timestamps or rough alignment of the action in a long video. And can we learn to then localize correctly the actions and learn a model for action recognition that doesn't need those expensive segments in a video? So you would start by saying, okay, there is an action, it's roughly around this point called open fridge, and you have lots of examples of this type of action. You train your initial classifier with random frames around this single timestamp, some very noisy, and over time you basically refine your proposal of where the action is, and you refine your model. So it's like an iterative process of I'm changing where the action is, the ground truth, and I'm changing the model until you converge into the right action. And it was very interesting to see how the model converges. So this is an action of taking glass. And after refinement, the refined action was really very short, a lot shorter than our typical start and end times that we've been labeling over the years. So this is, again, moving the bottle. And if you actually look at the refined action, it's really very, very short. And that raises the question of whether what we have imposed on our systems as start and end times is really what the systems want or need, because they were here picking up the most discriminative part of the video. Over the years, we've addressed a bunch of these research questions. I'm just kind of plotting the scope of what my group has been working on, and I'm going to be telling you about some of these actions, some of these papers, none of them in too many details, but really kind of giving you a broad understanding of the questions we have been asking, as well as others. And the first types of work we looked at was understanding skill. And in that case, we looked broadly beyond Epic Kitchens as well as within. That means if you give people 2 videos of someone doing the same action in this case, copying this drawing of Sonic, and you ask them who is actually doing it better. That's a very broad term. What does better mean? People will actually agree. Everybody will say, the one on the right, definitely that person is better at this copying, drawing task than the one on the left. Interestingly, they might disagree at the why the person is better. So they'll say things like, okay, the strokes are clearer, or the eyes are giving the right expression. But they all agree on the fact that one is actually exhibiting a better skill in drawing. So we collected these pairwise annotations from Mechanical Turkers, and then we started training a model. So this is the input. The input is 2 videos of the same action where a human has labeled one as exhibiting a higher skill than the other. And of course, what do you start with? You start with some feature extraction, some backbone. It's a bit of a long video, so you might want to do some temporal aggregation, and then you train a ranking loss. So you say, a human told me this person is doing better. The model should replicate that. So the score of person 1 has to be higher than the score of person 2, and with all possible pairs, the system does indeed learn. Of course, the biggest thing in these long videos is that not every part of the action is relevant to skill. These are videos from YouTube of someone braiding hair, and most of the video is just combing or doing some irrelevant things to action. And of course, at the time, this is CVPR 2019, we just added some sort of a learned temporal attention, so the model actually learns to attend to some part of the video more than others. And we added some sort of a loss, the stabilization loss, because data sets were not big, saying your learned weight has to outperform average weighting. And that did really well in making sure that multiple runs achieves they don't get stuck in local minima. And interestingly, after we've done that, we were getting really good results. But the system was not picking up errors as things that the system should make high attention to, which is crazy for us. Like, if someone is making an error, that should be the best possible measure that they are definitely not exhibiting a higher level of skill. And we realized the nature of these CMEs networks with shared weights doesn't really allow you to pick on these errors because they are shared weights. So they're looking at the common action between the 2 videos. So if something is uncommon, it doesn't get picked up by design. And the simplest effort here was to add another attention module, and until now they're exactly the same, they will learn exactly the same, but we make them specialize by a loss. We tell them one of your several attention weights, or heads now, they should attend to what's good in the video, and the other should attend to what's problematic in the video. And by having that specialization, we were able to pick all those interesting things. So this is what the system is picking as evidence of low skill. For example, in the middle line, you see someone undoing their makeup, or in the origami, you see someone unfolding. And these get picked up by the system itself. And of course, you can look at the high skill attention weight, and you can see the origami where someone is actually firming their fold as evidence of high skill. And I always use this work as an example of how machine learning has transformed computer vision. Because in the drawing, the system is picking up hesitation, pausing to think, as evidence of high skill in drawing. While in doing makeup, it was evidence of low skill. And these are things we could not have, like all our handcrafted, designed concepts. We would not have even guessed these things if we continued to kind of enforce our understanding of what the activity should be like. In all the works I'll present, if you want to know about the data sets and the code, you can look at the relevant web pages of these papers. Okay. So I'm jumping from how well you're doing something to how can you deal with multiple modalities. And simple fact, if you train your system in one of our Epic kitchens, and this work we were using the 2-stream architecture, popular until a few years ago, where you have RGB and optical flow, and then you train on one kitchen, and you try to test the same setting in another kitchen, we all know this doesn't work. The models don't generalize. And if you plot the RGB features, they don't even align, right? They're living in completely 2 different spaces. And of course, unsupervised domain adaptation is about this idea of having access to images in the second kitchen without labels. So we have these 2 kitchens, one with labels, one without labels, and the paper proposes a method for self-supervision as a way of aligning these two. Self-supervision, when you have multiple modalities, there are lots of ideas, but the most common one is, do these two modalities come from the same point in time, the same action, or do they come from different actions? And that doesn't need labels, right? You can take even the new kitchen, and you can say, are these from the same action or different actions? And you're training purely a binary classifier of same or different. And only by doing the self-supervision, you see that this big mess of red, which is from the new kitchen, is now being clustered in nice actions. So it's actually putting stuff together into nice clusters. They haven't yet aligned nicely, but you can do some sort of adversarial, so a gradient reversal layer that says, okay, I now want to just align them. I shouldn't be able to distinguish between these two kitchens. And that gives you the outcome we're after, the outcome on the right. So these are two examples of someone cutting. You can see that the object they're cutting is different, the background is different, the chopping board color is different. And if you again train in one kitchen and try to recognize in the other, they are living in two different parts of the space. Purely adding self-supervision, they're getting closer. And by combining the self-supervision with the adversarial, you can correctly recognize the action of cutting in the new kitchen without having additional labels. And also we've added another modality, which is audio, and I'll show you more about audio later, where actually audio is again another modality that's very robust to changes in environment, particularly in kitchens. The sounds of cutlery and water is the same regardless of different kitchens. Right. So I've presented some works from 2-3 years ago, maybe give you an insight of the work we are presenting next month. Next month, yes, in CVPR. It's called UnweaveNet. And again, you'll see a thread, which is all of these ideas are coming from the data set we've collected. So in Epic Kitchen, if you look at someone's morning routine, they're walking into the kitchen, they put their bread in the toaster, they start boiling the water for coffee, and then they realize there is some dishes they've left from the day before. So while the water is boiling and the toast is getting ready, they go and wash the dishes. And then once these are ready, they come back to preparing their breakfast and their coffee, et cetera, et cetera. And we kind of said this means that people are actually doing multiple possible goals in parallel. And we're really good in doing that as humans. Methods aren't even considering this shift between goals or between high-level activities. And we were wondering, could there be an approach that actually takes a video and does this? Say, okay, this is task one, and the person is shifting, and then they're coming back and resuming their activity after a pause. And to our surprise, we didn't find any works that are attempting to do this resuming activities after a pause. So we wanted to do something we call UnweaveNet, so a network that basically starts at the very beginning in an online manner, and then builds a memory, which we call the thread bank, a memory of the location. So it starts by adding a clip to the thread bank, observing the next thing and saying, is it a continuation or a start of a new thread? And over time, it's just building this understanding of the world where it's labeling things, say, with colors. We're not adding semantics. So we're not adding the word coffee or toast. We're just kind of understanding the groupings of these tasks. So this is a video through the eye on UnweaveNet. You'll see the video name and then the ground truth, as well as what the model is saying, which is the probability of which thread does this belong to. So it starts by saying, okay, I see what the person is doing. And then as soon as the person starts moving into another task, it's actually kind of saying there's more chance that this is a new thread, and it's producing a new thread as the person is kind of taking stuff from the kitchen and serving the food. And interestingly, even until you serve, it's fine. But this is the bit where the person is clearing. And they're saying, okay, the person is now clearing. So they're recycling. And it's learning to saying, this is a new thread or a new task. Right. So how do we do this? And again, we're inspired by lots of works in machine learning in general and AI. And we designed two things: a controller that decides what to do with the current thread, and a memory update. The controller is a transformer. What it does is that it looks at the thread bank. Say, in this case, the thread bank has 3 threads up till now, and it has an embedding. It learns an embedding of these threads, an embedding of the clip. So this is the thread embeddings. Oops. No? Interesting, okay? Yeah. A thread embedding, a clip embedding, And this is a token, a learned token. Think of learned positional embeddings, a learned token for a new thread. And it learns this transformer, which is then informing what do you update? To which of these threads does this thread belong to? Importantly, this has to be learned end-to-end. Because, what is a thread or what is a clip? This needs to come from the understanding of the clip features. And at each point in time, you train this model using teacher forcing, which is very popular in language models. That means you fill the thread bank up till a point T with the ground truth, and you only train for this current time using a loss that says you should predict the correct decision now. And by grouping all these thread times, really teacher forcing does a great job in dealing with long videos as well as videos of different lengths. And in this work, of course, you can't have enough labels. These are like very long videos. So we started by self-supervision. We actually faked it first to train the model end-to-end. We sampled randomly. We said we wanted 3 threads, and the first thread will have 3 clips, the second will have 5, and the third will have 2. So we sampled lots of these fake numbers, and then we position these inside the videos. So we basically take one video and say, okay, thread 1 will be taken from here, thread 2 from here, thread 3 from here. Making it within the same video makes it a harder task than if you brought stuff from different videos. And then we position these with some gaps between the threads, random gaps between the clips, and then we basically woven them artificially, creating these synthetic stories. But with self-supervision, because they're synthetic, we have the ground truth. So we have, this is the ground truth, this is a new thread, or this is resuming an old thread, another new thread, etc. And we can train on thousands and thousands, tens of thousands of these synthetic stories before going and refining on a small number of labeled sequences that actually show correct jumps between correct actions. And this was small enough that we could label it. So we have around 1,000 stories from actual videos, but most of the effort of pre-training comes from the self-supervision. So let's look at the output of what happens in UnweaveNet. We actually can, this is again the crib index, the ground truth, and the decision scores. We're having UnweaveNet correctly recognizing that the person is continuing an action for as long as they do, including when they're doing large camera motion, like the stretches of the pizza dough. The bits we want is this, is noticing someone dicing meat, then they realize they want to rinse the cleaver, and they come back to dicing meat. Notice that the sentences we're writing at the end is just our interpretation of the colors of what UnweaveNet analyzes. Or things like this, where somebody sets the washing machine, they throw the bottle, then they go to wash their hands. You can look at the paper for more examples, but of course, nothing is perfect. UnweaveNet currently over-segments, so it produces a few more threads than it should, and as well as sometimes starts a thread at a different time than what the human thinks is the shift or is the start. But again, this is a new idea, and we think it kind of changes the way we look at videos, thinking about online and thinking about understanding those transitions over time. Importantly, you can see the importance of self-supervision. I'm not going to describe these different metrics because these are clustering metrics. Teacher forcing accuracy, the middle one is just accuracy at a point in time. And in this case, you compare the self-supervision with just training with our small set, that's AS, and the final outcome, which is combining the self-supervision with the training. Okay, so I'll just get some water, give you a breather before, if you have a question in mind, maybe write it down because I'm going to overwhelm you with a few more papers before we conclude. Right. As I told you, we collected these videos along with the sentences. And these sentences were short, like, put the garlic down. And typically, when you take these clips, you take a video, you take that text, this is called cross-modal retrieval. What does that mean? You can either have the video and then have a big list of all possible captions and then try to retrieve your correct caption as close to the top of this ranked list as possible. So this is video to text retrieval. Or you can do the opposite. You start with your text, and you have all your clips, and you try to retrieve the correct video as close to the top as possible. And this, by design, is a well-known task. Typically, it's done on what we call trimmed videos, so short videos that are doing one particular task, say kinetics, and we want to do it with these fine-grained, longer videos. And in this work, part of a mission we've had is to understand what does the action put mean without knowing what the person is putting. What does the action open mean without knowing what open really is? So we decided to split this space of possible texts into a verb embedding space and a noun embedding space. That means we're parsing the sentence and completely separating the verb from the possible nouns. So in the first space, we're trying to get this video close to the verb put and further from other verbs like open and take. And in the bottom one, it's closer to meatball and dough. And then we still want to do the standard task of text video, so we can combine the outputs of these embeddings. Okay, is this working? Yeah. Combine the outputs of these embeddings to produce a big action embedding space where we relate the full sentences with the video clips. But going via these multi-view aspects of the word from part of speech gives us really cool additions, including zero-shot learning, because now I know what put is regardless, and I know what meatballs are regardless of the action. So basically, everything looks the same, except that the same video is undergoing two separate projections. One, a projection that's related to nouns, and one, a projection that's related to verbs. And the model has to learn all these jointly, but critically, it needs to go via the part of speech retrieval things. And what it gives us, if you look at one neuron within, say, the noun embedding space, you see that it's figured out all these possible things related to cutting board, whether you're washing it or cutting on it or moving it. And then from the opposite thing, you look at the verb embedding space, and it's clustering opens and closes of different objects, which is our aim, really, knowing what open is regardless of the object and producing zero-shot outputs. On the same trend of looking at parts of speech, one of my favorite works is looking at adverbs. We don't have adverbs in Epic Kitchens because people don't describe things with very long sentences, but we have them in how-to videos, where someone says, now you turn the bowl slowly, or now you have to fill this partially, or dice it finely. And these adverbs are a great way of understanding that you need to do something in a particular manner to satisfy the goal. So what do you do with these adverbs? There were prior brilliant works in adjectives on objects, which we kind of built on. So what we have is a video, and we have a narration, which we parse, producing the action, say rolling, and the relevant adverb, say quickly. And our objective is, again, to build an embedding space, to make sure that the word rolling is embedded via sort of a word embedding space. We want to embed the video, but we want to embed it not only close to the word rolling, but close to this modified word that makes rolling quickly, right? And that, what we call the action modifier, is shared across different actions. Of course, life is hard. We don't really have perfect aligned videos, so we had to do some sort of an attention to first figure out where in the video the action rolling is. So this is the action being used as a query. And then you're using that to figure out where the action rolling is, and then embedding that attended video close to the intended rolling quickly position in space. And the outcome is really cool, because what you do is now you have a video, and then you first say, okay, there is a mixing action. Where is it in space? So it goes, and the thickness of the border is the localization of the action. And from that, once the action is localized, it's trying to predict that adverb. Say the action quickly. Okay, I'm here. I just want to show you some of the more. So this is, yeah. So this is turning something quickly, and again, it's trying to figure out of this video where the turning action is. So it's no turning, and then once it turns, it's kind of recognizing that there is a turning and predicting the adverb. Right. I hope you're still awake. Coffee is coming at some point in time. But I want to tell you about audiovisual. And when I started doing Epic Kitchens, before Epic Kitchens, and some of you here come from the multimedia background, I used to tell people, I do computer vision, I don't do audio. Let's focus on vision. Vision is enough. And then Vangelis, who's the PhD student who's now graduated on all these works, he came and told me, we're not going to get accurate start and end times unless people can hear the audio. I'm like, what do you mean? Because we were hearing these things of starting the coffee machine, starting the tap, and once you hear the audio, the accuracy of the start and end time was drastically improved. And that changed my perspective. I'm like, okay, if human labelers need that, why are we denying the machines the idea of actually looking at audio? And I realized audio generally tends to be speech. If you look at audiovisual, it's mostly speech or musical instruments. And we were dealing with a completely different beast of audios. And I hope this will work now as you hear what type of audios we have in Epic Kitchens. I'm calling these object-object interactions. All of you know what that really means, but we can't describe it using a clear word. Then we have lots of material sounds. Things that really what the material of the object is. And we have sound-emitting objects, i.e. machines. And these were the types of sounds we were actually trying to use to recognize actions. And this took a number of years until we realized there are really two types of sounds in these data sets. One we call harmonic sounds. So this is the sound of water. You can hear a particular frequency, and it's continuing over time. And the other are things we call percussive sounds. And these are two different beasts, really, in what you can look at and learn from. And with time, we realized this is not only in Epic Kitchens, so going into other event data sets, we found similar breaks. Sound of rain on the left, and a typing machine on the right. So in this work, which we submit, it was the only work I've ever submitted to an audio conference, and they really, really liked it. So that's a good lesson for the future. Try another community. Maybe they like your work even more. And we looked at basically having two streams looking at these two different types of sounds. So how can you specialize? You actually look at the various types. So one of these, which was called the slow stream, which we wanted to attend to the harmonic sounds, really has a small temporal precision, but it's focusing on the filters and the number of channels so that you recognize exactly the frequency. And the other is the one that actually is looking at these temporal frequencies, the temporal resolution. So it's smaller in channels and higher in temporal resolution. And this is inspired by the slow-fast architecture in videos. We have lateral connections, and importantly, we have what we call separable convolutions, because what you usually put into these convolution networks is a spectrogram. So one of its axes is time, the other is frequency. So they're not really, X and Y in space. So you really need to attend to them separately. And this work was really great. And then once we've done this, we not only got better results on the data sets out there, but critically, we were able to prove the initial motivation. We were able to show that the slow stream is in fact picking things like, horse neighing or zebra or these types of sounds and thunder, etc., while the fast stream is picking tap dancing and, the typewriter, etc. And we were super excited that recently DeepMind took this work and they published a paper that they say that the slow-fast architecture in audio is not only important for the types of sounds we were looking at, but they proved it's the best for speech, music, and environmental sounds. So, great impact. If you want, I'm confident in telling you that this is not only a good code, but a great model. So you can look at Vangelis's work to look at the code and models that trained on VGG Sound and Epic Kitchens. Okay, so in the next 10, 15 minutes, I'll be telling you about two things that are really critical to understanding these videos. First, of course, we use the word explainable. I say it's digging deeper into the outputs of your model. If we have a video of someone doing a task, we typically tend to put this video into a model and then predict the class. And what we wanted to look at in this work that Will has led is to look at how does the model make a decision from the individual frames of the video. So basically, if you don't see anything, you're going to predict the class with the prior probability. So 0 frames, prior prediction. But the frames that are part of this action contribute differently to the model prediction. Some are really critical to know the action. Some might be completely irrelevant. So what you do is you try that out. You give the model nothing. You give it 1 frame, and you see the impact of that particular class. You try to put 2 frames, 3 frames, and the difference between these predictions is really the contribution of those individual frames you've added. Of course, you have lots of possible combinations. Very importantly, we realize that sometimes some frames are actually harmful for the model prediction. So having them is actually lowering the probability of predicting the right class. And I remember when Will told me that, I'm like, how is that happening? And this is a great example. So you have a video, and the video is from the something something dataset, and the class is called show that something is empty. And the person implementing it, acting the action, is actually flipping something up and down to show. And those frames where the cup is upside down is actually contributing negatively to the class show something is empty, which makes absolute sense. And over time, we have a dashboard you can play with if you want. I'm realizing that our models are better really than they think. So this is from Epic Kitchens, and this is a video of someone opening a drawer. And the blue line here is actually what is the contribution of the frame to the verb open, as well as to the noun drawer in red. So this is a video from the dashboard where we're going over time, and you can see that the word drawer is only correctly recognized from the last bit when you see the full drawer, where the action open is only really high at the very beginning when you actually are opening the drawer. So even within the verb and the noun, those frames are contributing differently to the decision. And currently, we're asking the model to basically deal with both, which is challenging. And one of my favorite examples, which is cutting tomato, I don't know how clear it is from the video, but you see multiple peaks. And every peak in cutting is when the knife is on the tomato, and every valley is when the knife is off the tomato, which really looks like magic. Like every time it is high, the knife is on the tomato. Everything it's low, the knife is off the tomato. Our models are really trying their best to satisfy a very difficult mission we're giving them, which is a full video, and these individual frames contribute not really fairly and similarly to the action. So again, we collected Epic Kitchens, and even after we collected Epic Kitchens, people said, is there enough data in egocentric vision? You don't have cameras out there with humans, it's not YouTube, you're not going to collect enough. And thanks to an effort of lots of people, recently, I don't know if you heard about Ego4D, we have released 3,670 hours of video collected from 923 participants from 74 countries. And to me, the most impressive part about Ego4D is that we did collect this during the COVID pandemic. We're going to remember that as a great experience and a great collaboration amongst a number of universities led by really great people, including people from Facebook AI. So Ego4D is really, I'm going to tell you about how catastrophic this was. We actually put an advert out there. This is what we've done at Bristol. And then people had come to talk, we talked to them about the project, why are we collecting them? We asked them, what do they do in daily life? What can we collect? Because we didn't want someone to go and collect, arts and crafts if they don't do any of that. What are their hobbies? And then we posted cameras, that's the pandemic. We sent camera by post, it arrived to their houses. We did another Zoom where we trained them on how to use the cameras. And then we had 2 weeks, which could be extended, where they collected the footage. They would upload the footage. We would check that it's actually, sometimes people have very dark places. And then eventually they would get us the camera, we would get them the payment, and we would de-identify the footage, removing any faces or identifiable information. But taking us really out of the kitchen into the outdoors, to people doing other types of tasks, sports, gardening, and I think the potential of Ego4D for understanding long-term interactions is great, particularly that, again, this is very much multimodal. So we do have, is this working? Yeah. We do have audio. We also have some sort of a 3D space environment. This is done by people at Catania. Giovanni and Antonino are here. IMU, stereo, footage from multiple persons, and some footage with gaze. These modalities are not present in every video, but now with the number of hours out there, there is a lot of understanding of audio-visual, again, something we're very passionate about. This is a space where you have a 3D pose of the world, and you're tracking the camera. This is in a mechanic shop. So again, for people who want to do more tracking and understanding where someone is in space along with the egocentric footage. You have stuff with IMU data. And then you have also the stereo footage. This is done in CMU, where they wanted to see how much stereo is relevant. And then at Georgia Tech, where they collected social games with all the people in the room wearing cameras. Lots of things to explore, and they all have followed this idea of producing narrations, so sentences alongside this long, very, very long video. And I told you this is my dream, that this is enough for training, that you have this rough alignment and a full sentence. This wasn't done by the participants, this was done by an annotation company, but you have these long explanations, and they're very, very dense and very short. Currently, there are open challenges. This is the first time Ego4D is having challenges at CVPR. We have a joint workshop, first Ego4D and 10th EPIC workshop. To me, really exciting to see the whole community moving in that direction, and more challenges happening in ECCV. Before we conclude, I wanted to share with you, going back to EPIC Kitchens, we're trying to really dig deep into what models learn and how do they learn it. And that's only feasible if you have spatiotemporal understanding of footage. So this is coming very soon, I hope. This is pixel-level annotations of active objects in the environment as people deal with the world. These are semantically grounded, so you know that this is a fridge, but I'm only showing you the colored pixels. And over time, you see exactly all the active objects, as well as how people are doing tasks. And some of them, I get excited about this footage where you see an object being peeled or being cut into different things, washed, etc. And from these slightly sparse annotations, manually done, we're also having some dense annotations that are automatic and verified. And again, towards actionable vision, which is learning from something and being able to imitate. Some of what we're seeing in these dense annotations is, I think, really exciting. So again, this is true footage from people's kitchens, which we have first sparsely annotated, and now densely tracking all the objects as they transform and as they change their semantics. So for example, you have this butter. First, you call the whole thing butter, and then once you open it, it becomes package, and what's inside becomes butter. And then you have this butter slice that you're weighing, etc. Again, I look at this footage and feel super excited. If you are into, hard tracking, where you can see the butter being split into lots of pieces and then being melted and becomes liquid and then ends up, somewhere else, we're hoping that, again, this will open the prospect for more interesting types of things. I'll show you one more dense footage. This is work with Toronto and Michigan. Right, so I hope I didn't send you to sleep, but I wanted to really tell you something about video understanding and showcase that even though many of us are working in video understanding, what you can do with the footage really depends on the video source. Egocentric, which is my passion, this offers this unscripted footage with plenty of potential. Audio is really critical. Language cannot be underestimated in trying to explain and understand what's happening in this footage. I believe attribution methods, which are methods that explain what the models are doing, might change what we build in the next steps. What is this new architecture? And, for a few years, we had this large-scale data set, EPIC Kitchens, which we can confidently now claim it really has transformed what you do in egocentric. And now we have an Ego4D data set, and very, very soon we will have these pixel-level segmentations and hoping that more and more people will be coming from various fields, trying what we do in egocentric vision. And of course, I get the pleasure of coming and presenting these exciting sets of work, but this is an effort of a large team over time, including over the pandemic, working remotely and very actively to push this area of research. And their passion isn't any less than mine, and I'm grateful to each one of them for their contributions to egocentric vision and also to my understanding of egocentric videos. If you have any questions, let me know. If you're interested about any types of works, look at my webpage or the individual students' web pages. Contact us. We keep at least the Epic Kitchens email active, and we respond very, very quickly. And all the works out there are available with code and models that you can build on. And I'm really grateful you were here today, and I hope this was worth waking up in the morning. Thank you very much.
Thank you very much. Thank you, Dima. Thank you for the amazing talk. Is there any question? It's Fabio, okay.
Thank you so much, Dima, for the fantastic talk, and great to see so much passion into this topic. I have a general question, actually. I thought I would start with this. It's uncertainty. So I guess in some of these videos, some of this audio, the example you showed, the package, it's buttered, then afterwards it's packaged and butter. So have you thought about uncertainty? So I mean, you have talked about, I guess this includes a lot of work, self-supervised, supervised learning, the classical one. Of course, you can get uncertainty as the output. But sometimes the ground truth itself, the video itself, has got some uncertainty.
Absolutely, and I think it's part of the challenge and the opportunity. There is uncertainty, but there is amazing certainty. Like you give people these two videos, and you tell them in the first video what is butter, and they point at this thing with the package. Then this is open, and you tell them what's butter, and they point at the thing inside. And even though it's the same individual, they don't, pause to just say, "Oh, I said something else." Was called butter. And I think more critically for me, my favorite example is eggs, right? You start by an egg, which is unbroken. People call it egg. Then they break it. What comes out is called an egg. And what you have been for a while tracking is now called an eggshell. You can't call it an egg. It's like, it's definitely not an egg. And I think there are questions we haven't even thought about. And at which moment does flour become dough? There is a point where you don't know, but there is a point where you know this is not flour. No one will say this is flour. And I think this shift from uncertainty to certainty, I think is super exciting. Is like, because people are certain about these two ends, they might be uncertain in the middle. And I think thinking about, as we said, an action being a start time where any frame before it is irrelevant and any frame after it is relevant is completely useless. Because we don't have this frame where one before and one after change dramatically the semantic. We have a continuous flow of things, and it's probably our fault, people working in video understanding, none of our models have gone beyond the image level concept, because in an image you have a boundary, and like this is what's inside the image, what's outside hasn't been captured. But in videos, this is this continuous stream, and we're trying to deal with it as a 3D box. And the 3D box assumes that anything before it is irrelevant, and that's completely incorrect.
Thank you.
Yeah, so that's why we have these. At some point we kind of used some psychology, because I really didn't. I thought people in psychology might have thought about these things, and they have to an extent, not immediately applicable to us, but there is something that they call the point of no return, where you kind of started the action, and now you're committed. Like you're committed, you don't go back. And we labeled some of the footage with the point of no return. But again, we still don't know how to put this into the model, because the model still expects a 3D block. So there are two things. There is thinking about the labeling, but there's thinking about the models very, very differently.
Okay, thank you. Other questions? Please.
Sorry. Just a curiosity, speaking about psychology, maybe you haven't given this a thought. Don't people act differently if they know they're being recorded than normal? I certainly would,
Yeah.
at least. I don't know.
Only for the first 5 minutes.
Okay.
It's amazing, right? Especially if you are in your kitchen, you're doing stuff, right? You might, I always notice it. The first 5 minutes, people are thinking about what they do. And then after that, you stop doing that. It becomes very, very natural. Again, it depends on the setup. There are some setups that are very heavy that keep you conscious throughout. But some of the setups, with time, I've seen people very, very quickly getting into basically doing what they do, because how long can you continue acting, right? So yeah, you can notice it at the very beginning, and typically we tend to throw the first hour and just focus on when they actually are in the act.
More questions?
Thank you for your very good presentation and also your passion that you showed us. So I have also a very general question. It was regarding the audio part.
Mm-hmm.
How could you distinguish between the harmonic and the
Percussive. So
yes.
currently we don't distinguish, but we produce a model that allows to attend to these two things differently. So currently we're putting the same audio into both streams,
Okay.
but having a specialized set of streams allows you to then capture both types of audios.
But are there some kind of audios which are kind of a mixture of both?
Not really.
Uh-huh.
Not really. Not up to our understanding. And it's interesting. Yeah. So you would think that there should be, but really it's very clear because you're thinking about the discriminative aspect of the audio, and the discriminative aspect tends to fit into one of these two different types.
Thank you.
Last question? Yeah.
Very nice talk, thanks a lot. How are you dealing with the cultural aspect? You know, because a kitchen, well, in Italy it's like a church. Let's say it's a
Yes.
very in US it's completely different.
Yes.
It's true. A piece of butter is the same in US and in Italy.
Yes.
But the way you use it is completely different.
Yeah, and I think that's a very important thing. Interestingly, object interactions are less cultural than, say, social interactions, right? So you can recognize what people are doing in any kitchen. You might not know the names of things. But I remember, I think, correct me if I'm wrong, but I think someone, when we collected here in Italy, they told me, which kitchen? Like, do you want the kitchenette or do you want the kitchen of the cooking? And I'm like, what do you mean, which kitchen? Like, isn't there like one kitchen in the house? But apparently there isn't. So, of course, there is a lot of cultural aspects that are interesting. We are now looking at whether we have now footage from Rwanda and from India. And when I went and presented some of this work in India, they told me, come collect in our kitchens where everything is, one color, everything is metallic. They don't have this ceramic thing, like everything is metallic, all the sounds are different, all the actions are different. It's super exciting to look longer term, but I think the good thing is you do understand. For example, in social interactions, and we know that, you might not understand what these people mean with their, but in the object interactions, you do understand, you might not know the names of things, but absolutely, this is a very exciting topic, and we are looking into domain adaptation across different geographic scenes.
Okay, let's thanks again, Dima, and we are going.
Thank you very much.
Thank you, Dima. Thank you. We are going to the next session of the morning.
Yes, I understand that. I'm doing that as well.
Just a couple of minutes to switch. You can stay up, fresh yourself.
Tony appena possibile.
Classification training pipeline for embedded systems. The presenter is Kirill Prokofiev, and he is speaking to us remotely. Can you hear us? Hello, hello. I was given a go a bit early now. Can you hear us? Kirill?
Yes.
Great.
Can you hear me?
We can hear you very clearly. I
Okay.
think you are ready to go.
Yes. Thank you. Hello, everyone. Today I present the article towards efficient and data agnostic image classification training pipeline for embedded systems that I and my colleague Vladislav Surasov worked on. As you all know, image classification is a vital task in the computer vision field, but software results in that field are obtained by a fine-grained adaptation of all the training pipeline components to the target task. And in practice, a data engineer could not have enough resources to do it. And the wrong decisions on each step for algorithm preparation can hurt the resulting classification model performance or bring misalignments with the requirements to computational complexity and memory usage. At the same time, techniques and models which are successful on one dataset may not be on others, so they are not dataset agnostic. From the practical perspective, we added the adaptability to the optimization process, designed a robust initial learning rate estimation heuristic, adaptive scheduler, and curated a set of regularization techniques that suit well to the considered model architectures. We also proposed a way of applying deep neutral learning to reduce overconfidence of model predictions. And first of all, we should define an optimization task. We want to maximize the score that represents the expected value of evaluation training for algorithm applied on every dataset in our representative samples. So to validate the proposed approach, we choose 11 different classification datasets. We try to select images with different number of classes sizes of images, and of course, content within the dataset. To evaluate image classification models, besides commonly used top K accuracy metric, we also calculate mean average precision in the same sense as it's considered in the person re-identification field. We denote a set of C classes as a gallery and each of n samples in the evaluation set as a query. Then we have to rank the gallery by similarity with the query, compute the average precision of this query, and then collect the MAP. In terms of classification task, the similarity is the predicted probability of a class. And thus, computing average precision is straightforward, as it's presented in this slide. What about architectures? We choose MobileNet v3 and EfficientNet as the base architectures for performing image classification. The chosen models have a performance accuracy trade-off with relatively small number of G-flops, which is enough in most of edge-oriented applications, and perform well enough to compare it to bigger models. So our proposed training pipeline looks like this. We use no bias decay and twice bigger learning rates for biases to give more freedom for model in that direction. We use SAM, sharpness-aware minimization, is an extension to SGD. It allows to achieve higher results in the fine-tuning than SGD, while requiring 2 forward-backward passes of the model per iteration, training iteration. SAM tends to smooth out the landscape of target loss function, and sometimes it happens to obtain better minimum. But we also, of course, tried ADAMV as a base optimizer, but it performs worse, slightly worse in our experiments. The next thing is the angular margin loss as the main loss for the EfficientNet and for auxiliary model in the mutual learning setup. This is a proxy-based loss function that's widely used in the face recognition area. In case of 2 classes, we will have 2 prototypes for each class, and we want to minimize the angular between latent vector representation after CNN and corresponding prototype. Switching to this loss function help us sufficiently enhance MAP metric. We also, as it was said, applied this loss for auxiliary model in mutual learning setup for MobileNet, but with one sufficient change. We set the scale parameter to 1. Mutual learning technique implies mutual learning of a collection of simple student models. As a result, performance of each student individually is supposed to be increased. We directly apply these techniques to pairs of identical models, but unfortunately did not obtain substantial accuracy gain. On the other hand, this framework could also be used in different manner. If one of the students has a stronger regularization and trains slower than the others, it may prevent others from overfitting and softly transfer properties of its regularized distribution to faster student. For this manner, we set scale to 1 and margin parameter to 0. Such settings of the angular loss make output distribution of the slower model less confident, and it also pushes the faster model to output a smoother distribution, while strong discriminative properties formed by AM softmax are transferred to the faster model as well. And on the picture, on the slide, we can see that the overconfidence of the main model greatly decreased. Great. Then, to add adaptively to our pipeline, we propose to use a modified version of reduce aware on plateau v2, actually. In the reduced awareness plateau V2, we force learning rate decay if 75% of the maximum training length had been reached, but learning rate drop haven't been performed yet. This helps model to converge when average training loss, which we use a criterion for learning rate drop, is unstable. Also, we incorporated early stopping into reduced awareness plateau V2 if the learning rate was decayed to a predefined minimum value, and the best top one score in validation subset hadn't been improving for a predefined number of epochs, we stopped the training. Additionally, we use 5-epoch linear learning rate warm-up. This helps us to reduce training time in terms of epochs more than twice, obtaining even better accuracy than popular and widely used costing scheduler. Since SGD performance on a given dataset is highly correlated with the initial learning rate magnitude, we have to incorporate estimation of this parameter into our training pipeline. Fast AI heuristic can generate a learning rate proposal after performing several training iterations. But in our experiments, it tends to output too high values, which destroys ImageNet initialization, even if warm-up strategy is applied. To overcome this problem, we propose to fine-tune the model with a predefined small learning rate for one epoch on the target data, and then run the fast AI algorithm. In this case, the model would react to fast increase of learning rates more smoothly, and the algorithm will select a value, as you can see on this slide, a value, which is quite close to which we might obtain with the grid search. Yes, and for the fine-grained learning rate selection, we use tree-structured Parson estimator from the Uptune framework. We set optimization criteria as top one accuracy on the validation subset after training on the target data for several epochs. We use also median trial pruning criterion, which breaks a trial if the best intermediate results is worse than the median of intermediate results of the previous trials at the same step. Pruning heuristic also could be used for grid search, but TPE also generates location of the next trials based on the previous trials location, instead of a random choice or using a grid. So we trained all the models starting from the ImageNet for training weights. We consider the following training setup as a baseline. Training length is 200 epochs. Costing scheduler, SGD with momentum as optimizer. Training images are augmented with commonly used augmentations like random flip, random color jittering, random crop, and random rotation. Dropout with probability in 20% is applied to the classifier layer. And the learning rate is set as an average of optimal learning rates, which we obtained by grid search over all the 11 considered dataset for each model individually. So as you can see, our adaptive strategy is outperform our baselines. Also, top one scores by dataset are presented in this table, as well as comparison with other solutions. Our mobile net with free small with adaptive training outperforms both our baseline and one of the best publicly available repositories with advanced training techniques for mobile net with free small. Our next efficient net B0 with adaptive strategy demonstrate higher results on some dataset compared with bigger ResNet 50 from VTAP. And ResNet 50 from VTAP is trained with heavyweight search over hyperparameters. They considered learning rate estimations, schedule optimizers, batch size, training preprocessing functions, evaluation preprocessing, and weight decay. So to sum up, our simple and light adaptive pipeline perform well and is suitable for most edge-oriented application. So yeah, thank you all for attention. If you have any questions, please ask.
Do you know what the optimal number would be? How far are we? Like, could we, if we had found the perfect learning rate, the perfect initialization, what do you think the optimal number would be? Are we close to it or really far?
Optimal number of epochs. Sorry.
Yeah.
Okay, about epochs in our pipeline, they are not, they are, we choose a predefined number of epochs and set is to 200 epochs. But our adaptive training pipeline can stop training earlier than this number. Because of that, our pipeline can train a lot of smaller number of epochs than if we use some commonly used cosine schedule.
Sounds good. Any other questions? Great. Let's thank Kiral again.
Thank you.
On the second talk, Continual Learning with Neuron Activation Importance, by Suhi Kim, who's also joining us remotely. Suhi, can you hear us?
Yes. Do you hear my voice?
Yes, we can hear you very clearly. We're ready for
Professor, I have to ask you to move on the center of the stage because the microphone is on the center of the stage because the microphone is feedbacking into the speaker. Okay. Sorry, thank you.
Right, we are ready for your talk.
Okay, hello, I'm Suhi Kim from Korea University, and this is ICIEP 2021 presentation of our model for continual learning with neuron activation importance. Continual learning is a sequential learning scheme on multiple different tasks without accessing previous tasks, but keeping previous task knowledge. For example, a model learns to classify only people and dogs at the first training time and classify pears and apples at the second training time, and so on. After learning all tasks, the model should be able to classify what it learned, including people, dogs, pears, and apples. Thus, the goal of continual learning is to mitigate forgetting existing knowledge of previous tasks and to learn give a current task to the fullest. Also, a model should be robust to change in the order of tasks. However, we figured out that many previous methods have not considered the robustness of the order of tasks. As you can see the figure below, the classification accuracy of prior methods changes as the order of tasks change. There are three major categories in prior continual learning approaches. First is architecture modification of neural networks. Second is rehearsal using sample data from previous tests. And third is loss regularization to freeze significant weights of a model, calculating the importance of weights of neurons. Our method is based on loss regularization. There are three categories in weight importance measurement. WIWM calculates weight importance based on the measurement of the corresponding weight. NIWM calculates neuron importance based on the measurement of all weights. And weight importance is redefined as the importance of its connected neuron. NINM calculates neuron importance based on the measurement of the corresponding neuron. And weight importance is defined as the importance of its connected neuron. Our method belongs to NINM. let me introduce our proposed method. We penalize important weights of past tasks not to change during current learning. Essential neurons stands for the neurons important to all instances with large variation, and the neurons directly affect a given task. In general, we can define essential neurons as the neurons with high activation value to the majority of instances. In convolutional neural networks, activation value of a neuron corresponds to the average value of one feature map. So the average activation value of neuron corresponds to the average of global average pooling value. If we take neuron importances as the average activation value of neurons, then due to the difference in average activation values across the layers, weights of earlier layers tend to be considered more essential, as you can see the figure below. Thus, the task-dependent features, the features of later layers are less penalized not to change, and this makes a model vulnerable to changes in task orders. Thus, we propose to use layer-wise average activation divided by the respective standard deviations for neuron importance measurement to balance neuron importance distribution. And weight importance is assigned by the calculated neuron activation importance. Compared to the average activation based on neuron importance, ours prevents earlier layers from getting excessive importance compared to the other layers. So ours prevents a network from vulnerable to changing the order of tasks in terms of forgetting past tasks. Indeed, lower layer features such as edges are not task-dependent features. Therefore, we excessively freezing lower layer features is not preferable in continual learning. In general, if the essential weights of later layers of previous tasks change, the network forgets past tasks and hardly recovers previous task-specific features. On the other hand, even though weights of earlier layers of previous tasks change, there are other chances to recover general low-level features which are shared with following new tasks. Since our method puts relatively more constraints on the weights of task-specific features not to change than the prior methods, our method forgets past tasks less, showing stable performance along the change in the order of tasks. In continual learning, networks have to not only avoid catastrophic forgetting, but also learn new tasks. According to the extent of difference in optimal classification feature space of different tasks, optimized feature space in the previous task might be changed with a new task. We avoid a situation where the optimized weights for one task work as a local optimal for another similar task that may hinder new training from obtaining new optimal weights through weight reinitialization. In the equation, sigma stands for the importance of weights and W is the weight. As you can analyze it, whatever the magnitude of sigma is, the term is ignored if weight of past task almost equals to the weight of current task already in the initial epoch of the training of a new task. So this prevents the network from learning a new task. Thus, we reinitialize weights before every new task starts. We evaluate our methods on 4 different data sets: split MNIST, split Cypher10 and 10-100, and split Tiny ImageNet. For example, we divide 2 sequential classes of Cypher10 that compose each task and change the task order. So we have 120 different task orders. We define several evaluation metrics. Absolute task order indicates the sequence of the tasks that a model learns. For instance, task 1 stands for the first task that a model learns, no matter which classes comprise the task. Learning step-wise average accuracy, LA accuracy, represents the accuracy of each learning step averaged through the whole tasks involved. Degree of interference, DOI indicates the decreased extent of accuracy of each task after all learning steps are conducted. We use multi-headed and multi-layer perceptrons with 2 hidden layers with 400 value activation. The previous methods called as MAS outperforms all other baselines, reaching 99.81%, while ours achieves 99.7%. However, the accuracy is almost saturated due to the low complexity of the data. On split cipher 10, we use a multi-headed network with 6 convolution layers and 2 fully connected layers. Our methods outperforms all other methods and has lowest standard deviation of accuracy. Also, ours achieves lowest DOI. We also verified the effect of weighted reinitialization. The table right below compares the performance difference between applying and not applying weighted reinitialization. As you can see, accuracy increases in both methods when weighted reinitialization is applied. On split cipher 10-100, our method shows better stability, showing the best accuracy values in all tasks. On the other hand, previous methods seem to prefer to be better with recent new tests, proving that our methods based on continual learning is working appropriately. As you can see, the table, SI and MAS seem that they learn new tasks very well while forgetting what they have learned before. Since all incoming weights are tied to the neuron in our method, the higher number of weights to be consolidated during training new tasks causes lower accuracy of final task. However, in practice, the decrease of plasticity in our method can be addressed by using a larger network. Our network with double number of channels has improved accuracy, keeping its stability and better plasticity. Last, on split tiny ImageNet, we use the same network as split cipher experiments. In this evaluation, ours outperforms other methods as well. With that, I would like to thank you for your attention. So let me know if you have questions.
Thank you very much. Questions? So, quick question. So yeah, I'm not familiar with these types of splits. How do people select the classes in each task? Is it like randomly? Because I think if the classes are easy to distinguish from, the task might be too easy.
Yes, the classes are randomly choice.
Randomly chosen. And do you think the difficulty of the task matters here? Do you think like hard tasks should come first or easy tasks should come first? Do you have any overall ideas about how people should arrange these tasks for best learning?
I answer to this question. Of course, we are not sure about the difficulty of each task or each class, but of course, as you suggested, if there's a task which has more difficulty in classifying multiple classes, and then following task might be easier than that, then in that case, maybe some learning information from the previous task may help to be better in meeting with the next task. But on the other hand, if we have some easier task prior to some more difficult task, maybe this will distract may have some more difficulty. So that is the reason why we have sorted the order of those tasks to be fair in evaluating the performance of each continual learning method.
Yeah, fascinating. Yeah, this is a topic of my knowledge, but really interesting. Any other questions? Otherwise, let's thank Suhi again. Next Next, we're going into consistency regularization for unsupervised domain adaptation and semantic segmentation with Sebastian Scherer. And he's our third remote speaker. We have a fourth speaker in person. Save the person here to last. Sebastian, can you hear us?
Yes, I can hear you. Can you hear me?
We can hear you very clearly, and over to you.
And can you see my presentation as well?
We indeed can, yes.
Okay, so thank you very much. Okay, hello everybody. My name is Sebastian and I'm from the Machine Learning and Computer Vision Lab of the University of Augsburg. And in this talk, I would like to show you our paper, Consistency Regularization for Unsupervised Domain Adaptation and Semantic Segmentation. So first, I would like to introduce the problem we consider. So at domain adaptation, we want to adapt a model from a labeled domain to another unlabeled domain. And different domains can distinguish at image composition and style, for instance. And to make this clear, I have here two examples. The first one is very popular and is called the synthetic to real domain adaptation. The motivation here is that, especially at semantic segmentation, the annotation process performed by human is very time-consuming and expensive. Imagine that we have to assign a label to every pixel in an image. Synthetic data, on the other side, from games, for instance, can automatically be labeled and does not need humans to perform manual annotation. So instead of using a dataset with images from the real world, we can use a synthetic dataset with the labels to train our neural network. However, we are of course only interested in its performance at images from the real world, as we may use this model in practice. So at this problem, we want to adapt the model from a synthetic domain to the domain of the real world. And this problem here exists because neural network trained supervised on synthetic data perform usually worse on images from the real world. And that is because neural networks tend to learn features only from the domain on which they were trained. Another interesting example is the domain adaptation to different visual conditions. The famous cityscapes dataset, for instance, which shows images of urban scenes, is limited to some cities within Europe and only show situation at normal weather conditions and at daytime. A neural network that is trained on this dataset may perform worse at situation outside Europe, for instance, or at different visual conditions, such as situation at nighttime, foggy situations in winter where we have snow on the street, or rainy situations. So in both examples, we want to adapt a model to a new domain such that it also works there. And in domain adaptation, we usually distinguish between a source domain and the target domain. At the source domain, we have labeled data, and at the target domain, we only have images. That's why it's called unsupervised domain adaptation. And to perform such a domain adaptation, we usually have the following setup. So at the training of the neural network, we have access to images from the source domain and their corresponding ground truth annotation. And furthermore, we have images from the target domain, but of course, without any labels. And after the training of the neural network, we evaluate the network on annotated images from the target domain. So we use labeled images from the target domain only at the evaluation and not at the training. And such a setup is very typically for semi-supervised learning applications, where labeled as well as unlabeled data is used for the training. And because of that, the dominant approaches in this area currently utilize semi-supervised learning. And most work of semi-supervised learning, as well as our work, builds upon pseudo-labeling and consistency regularization. So first, what is pseudo-labeling? At pseudo-labeling, we simply use the model itself to obtain an artificial label for unlabeled data. So instead of using the annotation performed by human, we use the prediction of our model as supervision for the training. The key idea of consistency regularization is simply that a classifier should output the same distribution or prediction for different perturbed versions of an unlabeled image. And the key component here are the perturbations, which we will see later in our ablation study as well. These are used only when training on pseudo-labels from unlabeled images. And most research nowadays focus on different kinds of perturbations. And perturbations are usually manipulations at the image space. And here you can see our final proposed solution. It contains of two neural networks, a student network and the teacher network. In this configuration, the teacher network is not trained, so it does not receive any gradient-based parameter updates. The teacher is simply the exponential moving average of the student model, and the student model will be trained. And as you can see here, we have an image from our source domain. In that case, it's a synthetic domain. We can feed this image through the student model to obtain the prediction. And since we have the ground truth annotation here, we can simply calculate and train with the cross entropy loss. So that's the standard supervised training. Interesting is the semi-supervised learning part. So to obtain a pseudo label from target image, we feed them through the teacher model. And the student is finally trained on the pseudo labels produced by the teacher network. However, there are some further perturbations that the student has to overcome. The first is an image mixing method where individual parts of an image are replaced by another image. And to generate a sample for the student model, we take two images from the target domain, feed both through the teacher network to receive the pseudo labels of both images. And afterwards, we calculate the input and the target for the student model training by mixing the images and the pseudo labels according to this mask here. And the mask looks similar to a typical black and white skin pattern of a cow. So as you can see, mixing both images with the cow mask here, we get this image. This image is fed through the student model. We get the prediction. We do the same with the pseudo labels, and afterwards we can calculate again the cross entropy loss. Yeah, and this perturbation does not occur in reality, but it serves as an additional perturbation by suppressing areas, and they introduce an additional object boundaries at the edge of the mask. So the replacement of certain areas within this image here further results in some kind of object occlusion. So this perturbation makes it harder for the student model to predict the same pseudo labels as the teacher, since the teacher receives the clean images. As second perturbation, we additionally use dropout at the student model. Dropout also leads to a deterioration of the prediction, similar as image mixing, since only a part of the original network is used. And dropout has the positive effect here that the network can be trained on clean images, which lets the network learn particular features of that domain. Other perturbations, such as the image mixing method here, leads to some kind of unrealistic images. And in our approach, in the end, we finally use dropout and image mixing either together or one at a time. And both perturbations have finally in common that they make it harder for the student model to reproduce the pseudo labels from the teacher. Before I move on to the experiments, I want to say some words about the data sets we have used. So at the synthetic domain, we use the GTA5 data set. And here you can see an example image with its ground truth annotation. And since it comes from a computer game, we can automatically receive the ground truth annotation here. And as the name implies, the GTA5 dataset comes from the game of the same name. And at the real domain, we adapt the cityscapes dataset and the ACDC dataset. The cityscapes dataset shows situations mostly at Germany and at daytime. And the ACDC dataset further provides images taken at night, at foggy situations, rainy situations, and situation in winter where we have snow on the street. And these four conditions are not present at the cityscapes dataset. And for the synthetic to real domain adaptation, research community usually benchmark the adaptation from GTA5 to cityscapes. And we will further evaluate our solution. We further evaluate our solution at the adaptation from cityscapes to the ACDC dataset. In our experiments, we performed an ablation study to evaluate the effectiveness of each component in our approach and investigate how they contribute to the final performance on the synthetic to real benchmark. So on the left here, you can see that a model that has been trained poorly supervised on the synthetic data set achieves a performance of around 35% mean intersection over union at the cityscapes dataset. So as we can see, the model performs very bad at the target domain here. And with our approach in the end, we are able to improve the performance to around 53% mean intersection over union. And if we use pseudo labels directly without any perturbations, we only achieve a performance around 40%. Using dropout or the image mixing method alone as perturbation, we can increase the performance to 48 and 52% mean intersection over union respectively. So we can see here that the usage of perturbations lead to a stronger improvement when using pseudo labels and target images in general. And this shows that the used perturbations are indeed the key of the success of such methods. And combining both perturbations in the end, we can further improve the result. And also the image mixing method leads to some kind of unrealistic images. It leads to better result when using dropout, which we found actually very interesting. This shows that the model is still able to learn useful features from some kind of unrealistic images. At the right here, you can see our results on the cityscapes to AC/DC domain adaptation. So in this context here, the source-only model has been trained fully supervised on cityscapes, while the Oracle model here has seen the labeled cityscapes dataset as well as the labeled AC/DC dataset. So we have here the lower and upper baseline. Our method just uses the images of the AC/DC dataset, not the annotations. And as you can see, compared to the source-only model, we can improve the performance relative to the Oracle model by nearly 55%, only by showing images of the new visual conditions and without using any human annotation. And I would like to further notice that the ability of semi-supervised learning is to use unlabeled data. And this is not exploited in this experiment here, since the Oracle as well as our approach sees the same number of images during training, since the AC/DC data does not provide any unlabeled images. So if we could further collect more images, we may even further boost the performance here. So thank you very much for your attention, and I'll be very happy to answer any questions.
Thank you very much. Questions? Yeah.
Thank you for a nice presentation. If you go back to the slide with the ablation study, do you hear me?
Can you hear, Sebastian?
This one?
Yeah,
now I can hear you.
Yeah, okay. Indeed, on the right, you show the Oracle score. And what's the Oracle score for the left table? What's
Well, that's around 67% mean intersection over union. So that's just the Deep Lab version 2 with the VGG16 network as backbone.
Okay. And that's then when you do a training mixed with the synthetic and cityscapes. So this is then the score for pure cityscapes.
That's the score for pure cityscapes, 68, and pure GTA 5 is the 35% intersection over union.
But the combined, I think the question is, if you combine the synthetic and the cityscape.
Yes, you may be able to improve the performance at the cityscapes dataset a little, but the GTA 5 dataset is far more different as the cityscapes dataset, so you can't expect any good improvements when you combine both datasets.
Okay, thank you.
Any other questions? I have one. So you've used all your pseudo labels. Have you considered filtering the confident ones, and does that help?
Yes, we did this in a further research where we filter pseudo labels, and we have noticed that it does not really help, because even though the filtering of pseudo labels is able to select far more wrong pseudo labels as correct pseudo labels, we still have the problem that where we detected pseudo labels as wrong and it was actually correct, removing this sample from the training has a very bad effect, because these are samples where our model is bad in predicting them, and here we can receive a far better training compared to samples where the model is very sure that it predicted the correct class.
Yeah, thank you. Let's thank Sebastian again.
Thank you very much as well. I wish you a nice rest day.
You too. And in our last talk, Pruning in the Face of Adversaries, Florian Merkel, who is here.
Control L to go to full screen, please. Thank you.
Okay. Good morning, everyone. I'm here to present the work of my colleagues Max Samsinger, Pascal Schädtle, and me on the influence of neural network pruning on adversarial robustness. The outline of this talk will be as follows. I will firstly present something on adversarial machine learning, go into neural network pruning, present the experiments we conducted and the results, and finally the conclusions we can draw from this work. So in general, classification looks like this. We have an input image, which is represented in the input layer. We got a neural network with a couple of hidden layers and an output layer, and that makes a prediction on the class. And here we have our image, an image of this panda, and the network correctly outputs the prediction panda with a 58% confidence. So we have inputs and labels drawn from a distribution, and we got a classifier that maps an input image to a class, and we want this class to be the actual label. So the goal is correct classification. Now, in 2013, actually, Szegedi found that deep neural networks have some fundamental flaws. So what is it exactly? So again, we have the panda with a model prediction on the left. And then we have the same image on the right. However, for this image, the model actually predicts the class given. And to make it worse, it's rather confident for this class. However, I don't know if everybody knows how given looks like. Like givens actually look like this. So something went wrong. And what goes wrong there is actually that it's not exactly the same images, even though it looks like. But there is some noise added. And it's important to say that this is not just random noise, but it's rather calculated, as in this case, it's the gradients of the loss function with respect to the input image, or more specifically, it's the sign multiplied by a factor, epsilon. So our adversarial example is the original image and an added perturbation, and there's a distance, obviously, between the adversarial example and the original image, which is quite often in the form of an LP norm or distance, and we call it semantic preserving or imperceptible if the distance is below a certain threshold. And the goal of adversarial examples is for the model to misclassify the adversarial example and not assign the correct class. Some of the common metrics for the distances are the L0 distance. And here you can see an adversarial example that was crafted with an L0 distance optimizing algorithm. So you can see just a few pixels changed, hard to see in the image. And there's also L infinity norm optimizing attacks where all the pixels are changed. So this is magnified by, I think, amplified by the factor of 30 or something. Otherwise, it would not be visible at all. And L2 perturbations look like this. So neural network pruning refers to the process of retrospectively deleting parameters of a neural network with a goal of reducing memory and computational requirements, which is very important on mobile devices or on edge computing. So to illustrate this, you have this unpruned model on the left, lots of parameters, everything is connected, and on the right, the sparsified version with plenty less weights. Pruning methods are defined by several dimensions. One is unstructured, or the structure of the pruning method. So on the left, just single weights are removed, and on the right, whole structures are removed. In this case, it's neurons, but it could be filters or single kernels, and speed up and memory requirements or advantages in those terms are easier to realize with structured pruning. Other dimensions are the selection criterion, so how to choose the weights to delete. There are magnitude-based approaches, gradient-based approaches, and often random pruning is used as a baseline, which surprisingly works better than sometimes more sophisticated approaches. The scope, if you go layer by layer, or if you look at the whole network at once when pruning, there are iterative approaches and approaches that prune everything in one shot, and there are different reinitialization strategies. So when looking into the literature, there was this really good work of Alexander Madry's group on adversarial robustness, in which he stated this sentence, capacity alone helps. So in other words, the more parameters, it's not exactly right, but simplified, the more parameters the model has, the harder it is to fool, the harder it is to attack. And we were asking the question if this assumption holds true when the capacity is reduced retrospectively. So in order to find out, we carried out extensive series of experiments. We used 4 different CNN structures on different data sets with difficulty from lower to higher. We used the most important attack algorithms, the most used ones on the main distance metrics. We applied a total of 9 pruning approaches, unstructured, structured, magnitude, and random as a baseline on a wide variety of compression rates. And the evaluation pipeline looked like this. We initialized the model, so no transfer learning, which might make a difference. Train the model to convergence, prune the model, fine-tune. So it's an iterative process, evaluate the benign accuracy and the robustness, and do so for all compression rates, do so for all pruning methods and all models. And the measure we were looking in is robust accuracy, which is basically the fraction of samples from the test set for which the model returns the correct class when fed the adversarial example. So basically the rate of failed adversarial examples. So when we recall Madry, this is what we actually expected. So we got robust accuracy on the one axis and compression rate on the other, and we would expect a decline in robust accuracy with a decline in parameter count. But we are actually surprised to see something like this, where the adversarial robustness increased even for higher pruning ratios. But those are exemplary results for the large ResNet and for the Kalini-Wagner L2 attack. And for most scenarios, it actually looks like this, but this is still quite remarkable as the robust accuracy stays stable, and we will see later small increases for mild pruning ratios in almost every scenario. and it's the same for the L0 attack. So taking a closer look at the unstructured global magnitude pruning method, which performed quite well in our experiments, we can see that we have gains in benign accuracy for higher pruning ratios up to 8 and even beyond. And then when looking at the robust accuracy, it's a lot of numbers, but actually what matters are the bold numbers where we see an increase. And we can see that for a compression rate of 2, we have an increase in as good as all attack scenarios. And even for a compression rate of 4, it's balanced between small in and decreases before it sharply drops at a compression rate of 8. So while neural network pruning obviously has its major advantages on edge and mobile computing, it should even be considered when resource constraints are not a major factor and even if security is of interest, as it is possible to enhance the clean accuracy and the robustness simultaneously, which seems counterintuitive, especially with what Marjorie said. But if you think about it, adversarial examples are actually, the existence of adversarial examples are actually attributed to the high dimensionality and areas of that are ill-defined in the network. And when retrospectively reducing the capacity, we are actually trying to maybe delete those parameters that contribute to the existence of adversarial examples. And this is actually also in line with another work in our group where we found that mild pruning enhances the explainability of neural networks when explainability maps are shown to humans. So yeah, model compression and neural network seems to be not mutually exclusive. And this is what our work has shown. Thank you.
Excellent. You got a free tutorial on both adversarial and pruning. Excellent talk. Any questions? We have one here.
Okay, thank you so much for the nice presentation. I have one question about the pruning strategy you deployed. From what I could understand, it is something very general, and you just wanted to test how the robustness towards adversarial methods work. Do you think that maybe some pruning strategies specifically purposed for this specific task, so to be more robust towards noise, can be addressed? And in such a sense, how much do you feel the accuracy for the general task the model is going to be trained to will be affected by this? Thanks.
That's an awesome question. We were experimenting with looking at the activations that changed when feeding adversarial examples and benign examples and trying to prune those specific connections. Unfortunately, we couldn't get really good results there. Yeah, I was hoping for that, and it would actually make even more sense. But to be honest, like we might look a bit more into it. It were like really preliminary experiments, and we might look into that again. Yeah, thank you.
I was wondering if it differs which layer in the network you do pruning on. Maybe earlier layers don't have much an impact on adversarial, and later layers do. Is it easy to restrict your pruning approaches to certain layers?
Yeah, that's actually a really good input, and
yeah, that would be interesting. Any other questions? With that, let's thank Florian one more time.
Thank you.
And you all now deserve coffee and some cakes.